day. Okay, so we will continue discussing about curvilinear motion cylindrical components. Okay, so last time we have discussed about the 2D components, or also called as the polar components. Okay, so actually your cylindrical components, okay, so as I have previously said, can be also 2D or 3D. Your 2D is um, also called as polar components, in which you have R or radial component and you have theta or uh, your theta is the angular component. Okay, so we have this space or 3D components, okay, for cylindrical component. Okay, so let us consider this curve. Okay, so this curve is in space because similar to your rectangular component, it has 3 dimensions. You have, okay, so since this is your R, your UR is parallel to R, and your theta is parallel to your theta at any given moment. And then we have another third component, which is the Z component, which is also called as, let us say, a distance Z component. Okay, so therefore we have 3 components in this situation. So we have a radial component, or R. We have angular component, or theta, and we have a distance or displacement component or distance, okay, Z. Okay, so therefore your coordinates, your 3 coordinates will are theta Z. Okay, this is your cylindrical component. So unlike the polar components, it will only be R and theta. Here R, theta, and Z. Okay, so similar to your similar to your triangular, rectangular formation. But anyway, since we have radial and angular, it is actually a rotating motion. Only which that there is a displacement component in the Z component. This is actually the Z component. Okay, so, or the displacement. Okay, so the up and down displacement of your cylindrical components. Okay, so let us revisit. Okay, let us discuss what is its formula. Okay, so we should refer to this uh, figure. Okay, so I will erase this one. Okay, so you may repeat it. Okay, you may revisit this by later. Maybe if you replay this video, and if some things are not clarified in this portion yet, you can always revisit. You can always replay those portion in our video. Okay, so we have R, theta, and Z component. Okay, so when we talk about velocity, okay, so let's talk about velocity. Here are, okay, actually, well, since we have a Z component, so we'll start at, okay, this the S, or the displacement. Okay, so we'll start, since we have displacement, so we have the value of R. Okay, so here we have the RP. Okay, so your RP, okay, so is simply Okay, so this is actually a z component. Okay, so this is the axis z and r and z. So therefore, your rp is equivalent to r squared plus z squared square root. Okay, so that is in um, scalar form. In uh, in vector form, it will be r I, okay, I know r in u r u r plus z, okay, okay, so z u z. Okay, so this is in a vector component. And then we have, okay, so this is your displace for your r or radius. Then we have velocity. So for your velocity, we now have three components. So your velocity will be logically VR, UR plus VZ, okay, V theta, U theta, and then Z, okay, and then we have the Z component or um, the Z single dot or dz over dt, okay, Z differentiated first derivative of Z with respect to time, okay, this is also okay, multiplied by uz, okay, so therefore, okay, so please remember that Z single dot is equivalent to dz over dt, so therefore your V is equivalent to the square root of the sums of the squares of VR, okay, plus V theta, and then the dz over dt. Okay, so that is how it works. And then your acceleration will be in vector form, will be A is equal to AR UR plus U theta A theta U theta plus, okay, double dot C double dot UZ. Okay, your Z double dot is equivalent to the second derivative of Z with respect to time, which means your acceleration will be the sums of the square AR squared plus A theta squared plus dz over dt squared. Okay? So, in this situation, you will still use the formulas we had used before. So, it is still equivalent to this. Okay? So, your VR is still just like your 2D is equal to dr over dt. Or you can rewrite it as r with a single dot at the top. Okay? And then we have v theta. It is still equivalent to r times d theta over dt. Or r multiplied by theta with a single dot at the top. Which means this theta with a single dot at the top is equivalent to first derivative of theta with respect to t. Also for your acceleration. Okay? So, what we have previously learned from polar components is still applicable to three-dimensional space components of polar cylindrical components. Okay, it's just that we have the z component in addition. Okay, so we have d squared r over dt squared minus r times d theta over dt quantity squared, or r with a double dot at the top minus r minus time multiplied by theta with a single dot at the top squared. And also for your a theta, it is equivalent to r times the second derivative of theta with respect to t plus 2 times the single derivative of r with respect to t times the single derivative of theta with respect to t. Or you can rewrite in this following, it could be rewritten this way, okay? So, this is the formulas for your three-dimensional cylindrical components or 3D cylindrical components, okay? So, from this figure, okay, we have r, theta, and z component. So, I hope you understand, okay? So, this is still the formulas class, okay? So, we will have an examples in a separate set of videos, okay? So, if you want to understand the lesson better, okay, wait for those examples to be uploaded, okay? So, don't worry because I will put the links of those examples under this video, okay?